Welcome to the third part of Analytical Techniques and Quality Control. Learning outcomes for this session is to understand the qualitative application of thin layer chromatography, high performance liquid chromatography, and UV and IR spectroscopy for the quality control of active pharmaceutical ingredients and formulated medicines. Remember that qualitative analysis is used to find out if a substance is present in a sample. It's a yes or no analysis and rarely involves numbers. In our case, the qualitative analysis of medicines will tell us if the drug that the medicine claims to be or claims to have is the one that they say. And quantitative analysis will tell you how much of this drug is in the medicine or in the API, the purity of it in percentage. Many of the identification tests for APIs in pharmacopoeia are very simple. The pharmacopoeia tells you how to prepare and run the TLC experiment, and you can see in the table on the left. You always need to compare your API or medicine versus an official standard provided by the pharmacopoeia. You have to buy from them a certified material which is pure compound, and usually this is very expensive. But the analysis itself is really easy, as you can see in the plate on the right. The sample or the injectable containing bupivacaine is spotted 3 times, and then the standard consisting in bupivacaine certified material from the pharmacopoeia are spotted also 3 times. Once developed the plate, we have the average of the RFs very close. You can see that at the extremes of the plate by the sides, the spots go a little bit further. This is usual in TLC because towards the sides of the plate, the solvent makes like a U. And in the middle of the plate is the solvent front is more linear and stable. The absence of other spots in the TLC tells you that apart from bupivacaine, there's nothing else. So this is desiderable. So in this case, we will have a perfectly compliant product which we can put in the market. There is another type of analysis for the identity or test of drugs using thin layer chromatography that calls for using the standard of the drug, the certified material bought from the pharmacopoeia, which is the drug you want to measure in your medicine, plus another standard which we may call internal. Look, if you look on the table where it explains how to make the standards, the solution A is a solution of diclofenac, which is this drug which we want to analyze in our medicine. But then the solution B consists on dissolving a known amount of indomethacin in the solution A. So we end up with a solution which contains both diclofenac and indomethacin. What is this for? Well, the diclofenac and indomethacin have very close molecular formulas and structures. They will be only separated if the plate and also your way to prepare the thin layer chromatography are perfect. So this is a kind of double check that you are making the analysis according to very high standards. When you see now we have 6 times the SST solution. SST means standard. We have two standards now. So if you can see, the two drugs are really very close together, but still they're separated by a small white band, well, not band, but limit. This means that our plate and our way to do the TLC has been perfect, and it performs very well. It can separate diclofenac from indomethacin, and then we can see that the RFs of the spots in the middle part of the plate are perfectly aligned with the spots coming from our diclofenac sodium injectables. Obviously, our medicine doesn't have the second spot. The indomethacin shouldn't have any indomethacin, only diclofenac. As I said, indomethacin is just to check that the whole procedure is perfectly run and the plate is performing very well. The absence of other spots in our diclofenac sodium makes us to think that there's no major impurities and that the product is good to go to the market. However, testing for impurities of the APIs is better done with high-performance liquid chromatography, and this is mostly the method of choice for pharmacopoeias. Here we are going to explain how this is done. Well, we're going to take paracetamol as an example, and in the upper table on the left side, you have all the compounds that are listed in the pharmacopoeia as possible impurities of paracetamol. You see that they are identified by letters like impurity K, impurity B, impurity A, impurity H, impurity I, and impurity J. Well, these letters doesn't really match with the order of elution that you have in a HPLC, and rather they have been named with letters because probably A was discovered as an impurity earlier and then B later, and so on. The retention time of different HPLC are not exactly the same. The different machines have different performances, different lengths of KF tubing, so on, but still they should be quite comparable. If you can see here how they compare an Agilent 1200 series and an Agilent 1100 series. At the beginning of the analysis, the retention times absolute are away from each other by the order of a few seconds, but towards the end of the analysis, the differences are quite notable, in the order of 1.5 minutes. Still, for both machines, the performance and of the assay is valid within the limits of the European Pharmacopoeia. You should read the monograph, and it will explain at the beginning how you can make sure that your HPLC is fit for the analysis or not. Sometimes we have to operate not with retention times in absolute, but what we call RRT, or relative retention times, which is the table below the one we were commenting before. When you convert the retention times into relative retention time to paracetamol, the differences look like less big. They look smaller differences. Impurity K is up or down 0.01, and impurity J is just less than 0.5 or 0.4 units. That's probably a better way to talk about differences in HPLCs. When you look at the chromatograms, in the upper chromatogram, we have injected all the standards, which means the paracetamol certified standard from the Pharmacopoeia, plus all the impurities certified by the Pharmacopoeia and bought from them. This is, as I told you, quite expensive material. Below you'll find the chromatogram of our API. And surprise, we find all the impurities, but impurity F. Impurity F is not present in our API. Is this good or is this bad? Well, actually it's great. If the other impurities are below the levels the pharmacopoeia is asking, then our API is passing with flying colors because we managed even to get rid of one of the most common impurities, as you can see. So in this case, our API is ready to go to the manufacturing plant and make with it tablets or syrups or whatever you need. Let's see another example of a possibility of an API which shows an unknown impurity. So what do we do in this case? Well, in this case we have very little to do because this is not complying with the pharmacopoeia. You can have APIs with less impurities than listed in the pharmacopoeia, but not with impurities that are not listed or allowed by the pharmacopoeia. So in this case, our product is not complying. What do we have to do with it? Probably send it back to the chemical plant. They may choose to wash out this impurity by certain procedures, or drop to the bin all the batch, which would be very costly probably. Let's have a look at the application of infrared and ultraviolet spectroscopy for the quality control of medicines. Remember that infrared spectroscopy gives you information about the presence of functional groups. This is useful for obtaining structural information about functional groups in an unknown substance, but can be used to identify an unknown substance by comparing its higher spectra with no reference sample. The infrared spectroscopy is a qualitative method only. You cannot measure how much of the drug you have with it. Let's apply this to an example of phenacetin, which is a very similar molecule to paracetamol, which in our problem shows peaks at 1655, 1555, and 1513 centimeters to -1. We need to compare these values with reference bands in the infrared, these maps that tells you at which region different functional groups are associated with. Well, here we can see that in our infrared spectroscopy map, the region between 1655 and 1500 is actually containing 3 overlapping types of signals. The carbonyl of anamide, the NH bond of anamide also, and the aromatic of the stretch of the aromatic carbons in the benzene ring or in the aromatic ring. Whether one or another is the right one, you need to look at textbooks and libraries of infrared to understand. In this case, the 1655 belongs to the carbonyl, and then we have closer to each other the amine signal in the amide, and then in close to 1500 the double bonds of the aromatic ring. So it fits with the structure of phenacetin and is probably an identification good enough. It suggests to continue working on the identification of the drug with more costly methods. Now we're going to apply the infrared spectra as identity test in paracetamol. On the left side you have the spectra that we managed to obtain for our API. How do we know this is paracetamol? Well, we have always, as I said, compare with the spectra or the spectrum of a certified material. In this case, we can go to an online library and obtain the certified spectra for paracetamol and then compare to each other. Here we can see that actually the different bands that correspond to the different functional groups in paracetamol appear very clearly in the IR and match with the certified spectra we obtain from the library. The hydroxyl has a very prominent peak, very broad one. Then we have the amine, which is part of the amide, and this shows two peaks actually. One on the very left of the spectra and another one at the very beginning of the region showing the stretching peaks. Remember that in IR we have bending and stretching peaks. Bending a bond is much easier than stretching, so bending the bond needs less energy than stretching the bond. Finally, we can see the signal for the carbonyl, the stretching of the carbonyl bond in red. So we have proved that all the functional groups that should be present in paracetamol are present in the spectra. So we have a yes and a go to continue the process of identity with other more expensive procedures. But if this procedure was a no, then we would be saving time and money and not doing all the tests. Ultraviolet also gives information about the presence of functional groups, but also about their combination, as long as they are able to absorb light, ultraviolet light, and that's why we call these groups chromophores, that mean in Greek absorbing light or carrying light. Unknown substances can be identified, like we did in IR, by comparing the spectra with known reference samples. In UV, we have the advantage that this technique is not only qualitative but can be also made quantitative by using the Lambert-Beer law, and we will have a look at some examples in the next session. Look at the example below with paracetamol. Paracetamol can be split into three elements: a benzene ring, an hydroxyl, and an amide. All these three functional groups absorb ultraviolet light at different wavelengths. The benzene ring absorbs UV light at around 250 nanometers, while the other two functional groups, hydroxyl and amide, they do it at 220 nanometers. When you put together all this into paracetamol, you can see that the resulting UV spectra is showing the maximum of 220 of the hydroxyl and amide, the maximum at 250 or so of the benzene ring, but also a small maximum at around 290 nanometers, which is the combination of all these functional groups. So when you applied this ultraviolet test to a formulated product, you can see that in this case we have effervescent tablets and tablets. And paracetamol standard, all the three UV spectrum are almost matching perfectly. The intensity might be a little bit bigger or smaller, but the maximums are perfectly aligned. So for us, the identity test in these products, in these effervescent tablets and in the regular tablets non-effervescent, would be a go. They comply, they have paracetamol. So that was all about qualitative analysis. I hope you found it quite easy and straightforward. They are, as I said, they are just yes or no's about the presence of a drug. And in the next part 4, what we are going to do is to enter into the calculations of how much of the drug do we have it in the API or in the manufactured product. Thank you and bye.